What's here with respect to multiple linear regression? Let's see here. It is an extension of simple linear regression with two or more predictors. To plot residuals with fitted values, it will help us to detect, or we can say, the non-linearity or the heteroscedasticity. The model keeps on changing, right? So according to that model, we will be writing the proportion. So that is all about R square. Hello everyone, I welcome you all to the first session of Unit 5. So yes, we have completed 4 units, that is under NEP syllabus, and we are heading with the 5th unit. So yes, this is under our R programming, that is statistical computing and R programming, and the unit name is Regression Model and Advanced Graphics in R. Over here, my name is Deepa Kutnikar. I am working as an assistant professor under Department of Computer Science, Vidhyaashram, Temple of Excellence, MYSURU. So let's see what is the agenda of today's session. Yeah, in today's session, we'll be discussing like what is all about the simple linear regression. Then we'll be also learning like how to deal with multiple linear regression and what is the difference between simple linear as well as multiple linear regressions. Then followed by, we'll be learning like linear model selection as well as diagnosis. So these are the topics that we discuss in today's session. So let's begin our session. Over here, let's start with simple linear regression. Let's see the definition over here. So when we speak about linear regression, we'll be discussing two different terms over here. The first one is predictor variable and the next one is a response variable. So now let's get back to definition and understand over here. It is a statistical method where we use this to study the relationship between a single predictor variable. For example, we have considered X and a response variable. So there will be some predictor variable which also can be called as an ancestor variable. So that is derived from the ancestor changeable properties. Okay, so that is X and then a response variable. Response variable in the sense the variable that gives response for your predictor variable. Okay, by using this linear regression, we'll be getting a difference that how the terms will be coined by differentiating both. So this is all about our simple linear regression. The formula for this is beta naught plus beta naught into X. What is X over here? That is a predictor variable, okay? And epsilon. So epsilon is a constant. As you can note here, the relation is completely dependent on the predictor variable. So over here, beta naught is an intercept where we can say the value, it will be beta naught. When it will be beta naught? Only when the X value is 0. Then we have beta 1, right? So it is nothing but a slope where we can accept the change in Y per unit. Okay, so this is all about beta naught and beta 1. Finally, epsilon. Epsilon is all nothing but an random error term. Okay, so this is how we can go with a simple regression technique. Then, whenever we consider a regression, we have to consider some assumptions considering, yes, these are the things and according to these things, I'll be going forward. Or as we are considering predictor variables, right? So for that predictor variable, we have to define the assumption. Only then I can believe that my simple linear regression is working properly according to the considered model. So for that, this assumption plays a very important role. Okay, so let's see what are the assumptions that we have to consider over here. The first one is linearity. That is, relationship is linear. The relationship between the predictor variable as well as the response variable will be linear. Then it is independent of errors. We can say the errors will be very, very less. Okay, and the value, whatever we get, it is completely independent of the errors and it is a homoscedasticity. What we can say over here is it is constant variance of errors. So the variance what we will be define or consider, right? Normal variable. So that variable is a constant and it is with respect to errors. Normal distribution of residuals. So these are the assumptions what we make in order to go with simple linear regressions. Up next, it is all about the example. Over here we have considered a vector of x where we have the values that is considered from 1 to 5, then followed by y, that is 2, 4, 5, followed by 4 and 5. We are defining a model. So what is model? Over here we are defining that it is a linear regression LM followed by our y vector and x vector. So as you can see, we are considering a relation over here, okay? Then followed by, I need a summary of this model. It has to verify there is a relation between them, or we can say both are independent. How was it? So it will be considered or evaluated by this statement, and finally we have to get a summary. So this is a small example. Then what is final thing? We have to plot, correct? So we are defining a plot with x comma y, and the name of the plot or the title of the plot will be simple linear regression, okay? Then followed by AB line, okay? So this AB line gives us a value with respect to model, and the outer line will be in a blue color. So you can change it according to a requirement. You can change the color. So this is a small example in order to deal with simple linear regression, and please note LM is the keyword that is used with respect to linear regression. Moving forward, let's deal with multiple linear regression. So single linear regression, we know we will be working with only one predictor variable. And what's here with respect to multiple linear regression? Let's see here. It is an extension of simple linear regression with two or more predictors. So this is very, very important over here, as we can see multiple. So we can directly say we are working on multiple variables, and you can see the expression over here, that is y equals beta naught plus beta 1 into x1 plus beta 2 into x2, etc. plus epsilon. The only thing varies between simple linear regression as well as multiple linear regression is the number of the variables, except at all are almost the same, okay? And now we have to see, by using this multiple linear regression, how we can improvise our regression technique, okay? So that's why it helps to improve prediction accuracy. So we will be predicting the variable, correct? So by doing this multiple linear regression, we will be having a complete data of predictor variables, not only single predictor variable, but multiple predictor variables, because of which we can say, yes, the accuracy can be maintained, okay? Then we can understand the contribution of each predictor, okay? So over here we can say each and every predictor has its own importance, right? So it will be considered and the contribution will be highlighted and understood. So this is the main help or the intention to move with our multiple linear regression. So up next, let's see what are the assumptions. So even here, the assumption remains the almost same, and we have some more updated assumptions. So let's see, it is same as simple linear regression, yes, but also we have to include one more, no multi-collinearity. There will be no collinearity, and the predictor should not be highly correlated. So this is very, very important assumption. This is especially with respect to multiple linear regression, that the collinearity should be very, very less, and what we can say is the variable should not be highly correlated. Up next, let's see an example for this. So over here we have considered the multiple data, that is empty cars followed by model. So over here we are defining the model of a car, where again you can see here I am working with linear regression itself. So I am considering LM. All right. Now I have to give the data with respect to car, like the weight, the pollution, as well as the display, then followed by a data, like what is the final data I have to display along with this properties, followed by a summary of this model, so that it will be helpful to see all the data in a one go. So this is a example with respect to multiple linear regression. Up next, let's see the linear model selection. Now we have multiple linear models, right? Like single linear regression, multiple linear regression, and how is it to select the required linear regression for our requirement? So for that is we have to see how we can go with, okay? So let's see it. Adding one or more variable increases complexity, but along with that, we can say it may not improve the accuracy too. Alright. Up next, the criteria for model comparison. We have a small criteria over here wherein R square, okay. R square is nothing but a coefficient of determination and it is considered as a proportion of variance explained by a model. The model keeps on changing, right? So according to that model, we will be writing the proportion. So that is all about R square. Finally, next one is adjusted R square. If I'm not satisfied with the proportion, then I can adjust that too. So that is adjusted R square. Then you can see here it is used to adjust the number of predictors and the AIC. So AIC is nothing but Akai information criterion and the BIC, which is nothing but Bayesian information criterion, which gives us a lower values in order to indicate better model fit. So over here these are the AIK as well as BIC are the two different criterias, okay, which gives us a better result like through which model I have to move forward. So this is all about the model selection. So we have to see with R square, then I have to check whether the predictor is sufficient or I have to go with more predictors or adjust that. Okay, once we are done with that, then we can directly go with the AIC as well as a BIC models. So this is a procedure to find out which regression model fits best according to our requirement. Now, let's see the technique which is involved in model selection. The first one is forward selection and backward elimination, and we can say a stepwise regression. So, any one of this can be selected along with our simple as well as multiple linear regression. So, now let's see a small example. Over here, we can see here the step, correct, right? We are dealing with multiple things. So the steps is very, very important. The step of model is defined wherein it says like automatic stepwise selection is provided, which says that the automatic stepwise selection is also holds good. Up next, let's see over here the regression diagnosis. As we are done with the model selection, up next is a regression diagnosis. By using this, we can see that the model that we are using is a valid one and the assumptions what we are defined is also a valid or not. Okay, and the analysis, the plot residuals with fitted values, it will help us to detect, or we can say the non-linearity or the heterosidicity. So this is a plot residual with fitted values. Up next, the normal QQ plot, which is a test which is used to find the normality of our residuals. Up next, influential points. So whenever we draw points, we will be having multiple points, right? So through that points, we can detect with the Cook's distance too. By using Cook's distance, we can detect whether the points what we have considered is a valid one or not. Up next, we have a small example. As we can see here, it is completely dependent on the plot, correct? So I'm defining a plot of model 2 which gives a residuals of QQ Cook's distance. Okay, so not to worry, QQ Cook's distance is just a statement that is utilized in order to find the influential point as well as a normal Q points. Okay, so this is how we can go with the diagnosis of the plot whichever we have created based on the regression models. Yeah, up next, in the next session, we will be discussing advanced graphics in art. So this was all about today's session. Thank you.